Okay, so this is my fourth lecture and last one at the summer school on infinite Galois theory, and the main focus for today is to see how this topic shows up in various settings in number theory. Earlier we were talking about generalities, arbitrary fields, and their Galois extensions, seeing what the topology looks like from 2 points of view directly on the group, or yet last time embedding it into a product of finite groups and using a product topology. So now I want to focus on a few ways that this material actually directly comes up in number theory. So let's go back actually to the p-power root of unity extensions. And in particular, I want to go to something from lecture 1 and see how that can be explained using some of the topics that have been discussed since that first lecture. So we have the p-power cyclotomic extension joining all the p-power roots of unity. And we could describe the Galois group on this field extension in two ways. Either as a sequence of numbers, mod p and p squared and p cubed and so forth, where everything reduces to the previous thing. It should be p to the n minus 1, or n greater than equal to 1, n greater than equal to 2, I guess. And the very first term, that should have been an a1, the very first term is not 0, and so all the higher ones are also not divisible by p. Another thing you could do is you could write out these successive numbers in base p, and then everything would be consistent, and all the earlier digits would already have shown up before, and you're just adding on one new digit at every time, and so formally you get this p-adic expansion where the first digit is not 0. It's from 1 to p minus 1, and either way, you could describe the action of this Galois group described in these formulas on a p-power root of unity by raising to that power. So if it's a sequence of numbers, modulo powers of p, you raise to the power that's in the nth slot. If it's written as a p-adic expansion, you just raise to the power you get by chopping off everything after the p to the n point, because zeta p to the n to p to the n is 1, and so those higher terms really shouldn't matter. And in terms of p-adic numbers, what Liang was talking about, this Galois group is the units, the invertible elements in the p-adic integers, the numbers that have multiplicative inverses. So we saw in the first lecture that the numbers 5 and 13 as exponents on the two power roots of unity actually have the same fixed field. The group that they generate as exponents under iteration, they both have the fixed field Q adjoin I, even though these subgroups are not the same. They're both infinite cyclic subgroups of the Galois group, different subgroups with the same fixed field, and the general theory tells us that there's a one-to-one correspondence between the intermediate fields and the closed subgroups. And so in fact, what's happening here is that although the subgroups generated by 5 and 13 in, say, the two-adic numbers, the units of the two-adic numbers, are not the same, their closures are the same. The two-adic closure of every subgroup, of both subgroups, is in fact the two-adic numbers that start with a 1, and then the next digit is 0, and then everything else is divisible by 4. So they're the two-adic numbers that are 1 mod 4. So for example, 5 should be a limit point of this subgroup generated by 13, and in fact you can write 5 as a two-adic power of 13. So I've written that down there near the bottom of the slide. So with that choice of exponent, if you actually take 5 and raise it to the 1, to the 1 plus 2, to the 1 plus 2 plus 2 squared, and so forth, and look at the result, modulo 2, 4, 8, you'll see that it's 13 every time. It was very satisfying to check my work. I raised 5 to the 1 plus 2 plus 2 squared plus 2 cubed, and looked at it modulo 2 to the 8th, and bingo, the computer told me it was 13. So the computer generated x for me, and it confirmed that x was correct. So it's either correct or it's just giving me false information, knowing I'm not going to actually test this by hand. Anyway, so just like in ordinary calculus, or algebra, I should say, you can solve for x using two-adic logarithms. If 5 is 13 to the x, then x should be the ratio of log 5 to log 13 to log, oh, that's upside down. I'm sorry. that should be the other way. Oops. Log 5 divided by log 13. Okay, using two-adic logarithms. Right? And so, yeah. And so 5 really is a limit of powers of 13 in the two-adic numbers. So everything is explained. Different subgroups with the same fixed field, their closures have to be the same, and we can calculate it directly there. Okay, so I want to go over something I brought up at the end of last time with maybe a little bit more of a more nicely detailed diagram. So I want to describe how we can construct an extension of the rational numbers whose Galois group looks like the 5-adic integers, the additive group of 5-adic integers. So we know that we can compute an extension whose Galois group is isomorphic to the 5-adic units. That's just adjoining all the 5 power roots of unity. And so that group of 5-adic units splits as a little group of 4 elements of finite order. You could call them 1, -1, I, and -I, if you wanted to. And then an infinite topologically cyclic group generated by 1 plus 5. And in fact, that group is 1 plus the multiples of 5. And the little elements of finite order are listed there on the screen. You have 1, -1, a number of order 4, and it's negative. Notice if you add those, you get mass cancellation. They add up to 0. Those last two numbers, they're negatives, like I and -I. In any case, so what we can do is apply these elements of finite order as exponents to each of these 5-power cyclotomic extensions, which really amounts to saying, for example, on Q adjoin 125, this little group mu acts, and in fact, it's just 1 and -1, and since I'm working mod 5 cubed, 2 plus 5 plus 5 squared, 2 plus 5 plus 2 times 5 squared, excuse me, and then 3 plus 3 times 5 plus 2 times 5 squared. This is all mod 125, acting as exponents. And so that's what mu looks like when you only focus on the 125th roots of unity. And so when you take the fixed field inside there of this group of order 4, when you reduce those mod 125, they still stay different. You have a group of order 4, and it cuts out a subfield, I wrote there as k sub 2, of codimension 4 inside the field, and of degree 25 over the rationals. And so you can see what mu fixes inside each of these 5-power cyclotomic extensions, and you generate the sequence of fields all over Q that are Galois, whose degree is successively higher and higher powers of 5. I should have put that 5 over on the... and these Galois groups, you just using the unit mod powers of 5 by this subgroup mu, and you're left with a cyclic group of order, well, 5, 5 squared, 5 cubed. So if you take the union of these fields, each is inside the next one, then the Galois group at every finite level is cyclic of order 5 to the n, and at infinite level, the Galois looks like the additive group of 5-adic numbers. It's not literally the additive group. It's really, maybe I really should put it this way. What it really is, more directly. Can you still hear me, Alvaro? Alvaro?
Sorry, I can hear you, but I lost the image.
The image?
Yep.
Hold on. Let me put the image. Can you see it now?
Not yet.
Not yet.
Might be coming up.
Can you see anything? What can you see?
I can see nothing. It's like you're not sharing.
Okay, hold on a second. Hold on a second. Let me go back. Share the screen. Start. Okay, is that better? Is it back?
No. Oh,
Yes,
it's coming.
no?
It's coming up.
Can you see it? Can you see the screen? Okay. So what happened was an error message came up and it gave me two options. It said something, there were two options, and I realized that I accidentally hit the wrong thing. And
That's okay.
so, yeah. All right. So the actual Galois group here is more like 1 plus 5z5. And this just happens to be isomorphic. Well, no. Okay, here, let me just, I mean, when you're modding out, okay, sorry about that. Like in Galois theory, when you look at the fixed field of a subgroup, the Galois group is really the quotient by that. And so anyway, so that's isomorphic to Z5. It's 1 plus 5Z5, which is isomorphic to Z5 by the logarithm. So it's very similar to what I mentioned on the previous slide. Whoops, where was that? Oh, I don't think it's there. Anyway, so this, yeah, so, right, so this big field union of all the blue fields is an extension of Q whose Galois group is isomorphic to the additive group of five-adic integers. Okay, so let's do it for a general prime. For every prime P, the group of p-adic units has a little group of finitely many elements of finite order, like 1, -1, and it could be some more things. And it always splits off as a factor. You have a direct product decomposition of topological groups. The other factor is not literally ZP, but it's a multiplicative group that behaves like ZP, just like when you take the non-zero real numbers, you can split it up into plus or minus 1 times the positive real numbers, and then using logarithms, the positive reals under multiplication look like the reals under addition. So that's kind of the same thing of what's happening here. And so if you take this little finite group of elements of finite order inside of the p-power cyclotomic extension, and you pass to the field that it fixes, so I call that, on my slide, I call that kp infinity. So this field is an infinite extension of Q, and under the Galois correspondence, underneath Q adjoins zeta p infinity, it has fixed group. It's fixed by mu by definition, and therefore its Galois group over Q, because everything here is an abelian group, so everything's normal, everything's Galois over Q. Its Galois group over Q is the quotient of ZP star by mu, and that's isomorphic to the additive group of p-adic integers. Okay, so that's what I have there in red down below. And so if you wanted to understand this subfield structure of this mysterious big field, kp infinity, well, you want to know what are the closed subgroups of the p-adic integers. Well, it turns out, of course, 0 is a closed subgroup, if we're writing things additively. And then if you multiply ZP by powers of P, that shrinks the whole group down a little bit more and more. So we have ZP contains PZP, contains P squared ZP, and so forth. Everything intersects at 0. And so it turns out that the closed subgroups of ZP are only these groups, 0 and ZP multiplied by powers of P. And so what that means is, aside from 0, every closed subgroup is open in ZP, and therefore, aside from the top fields, kp infinity, every subfield other than the whole field is a finite extension of Q, and it corresponds, it's of degree 1p, p squared, p cubed, and so forth. So you have this tower of fields, Q, kp1, kp2, and so forth, each of p power degree. Okay, and their union is the whole thing. So their union, in fact, is exactly that. Okay, and in fact, very interestingly, there's a conjecture of John Coates. If you know some algebraic number theory, this is a very interesting conjecture that all of these fields inside of these different ZP extensions of Q, all of these number fields should have class number 1. And so this is interesting because it's never been proved that infinitely many number fields have class number 1, even if you assume the Riemann hypothesis. And while we expect there are infinitely many quadratic fields with class number 1, we can't point to a proposed actual infinite list that should only have class number 1. But this is an explicit description of a list that is expected to have class number 1 all the time, although the class number calculations are really hard. If you look at those math overflow question numbers and search on them, you can find some discussions of that. So it's kind of an interesting role for these fields. Potentially could lead to a solution of the class number 1 question for finding infinitely many fields of class number 1. Okay, so we saw an example of a ZP extension of the rational numbers. So what about other number fields? Well, you can just take a composite. So if you, Alvaro, are you still there?
I'm here.
Okay, fine. So if you took any number field, F, anything of finite degree, and you saw how does it compare to the ZP extension of Q that I gave you before? Well, Galois theory tells you if you take a composite of a field like F over Q and a Galois extension like KP infinity, you get a larger field that will be Galois over the other field, F in this case, and the Galois group will be isomorphic to the Galois group of the original Galois extension on the right side, KP infinity, over the intersection. Now the intersection, I don't know what it is, but it's a finite extension of Q, so it has some finite degree, and therefore by Galois theory, the Galois group corresponding to this, this is going to be fixed by P to the n ZP. And so the Galois group of KP infinity over that intersection for some n, who knows what it is. And so therefore, this Galois group here, just like in finite Galois theory, you can kind of do this translation stuff. This will be isomorphic to ZP because all closed subgroups inside ZP other than 0 are actually isomorphic to ZP. And so in this way, we get a ZP extension of F, taking the composite with the ZP extension of Q that I constructed before. So this method, which could be described also more directly as adjoin all the p power roots of unity to F, that is, and then look at the fixed field by the elements of finite order inside that Galois group over F. So if you adjoin the p power roots of unity to F, you might not get all the p-adic units, but if you mod out by the elements of finite order, you will get a subgroup that's isomorphic to ZP. So you could describe it in a more direct way without taking the composite with the extension of Q first. In any case, so this construction is called a cyclotomic ZP extension of F. All right, so we had the cyclotomic ZP extension of Q, and then by taking its composite with any other finite extension of Q, or a more direct construction, we get a ZP extension of every number field. Now it's natural to ask, are there more examples? Well, yes, and it's hard to describe them. So you can't really construct other examples in an easy way over general fields. Over imaginary quadratic fields, there is a special technique, but over general fields, this is really about the only general method, maybe because over Q, it is the only thing that works. So it turns out that if your finite extension of Q, F, is not a totally real field, meaning its embeddings into the complex numbers don't always land in the real numbers, so like Q adjoin the cube root of 2 is an example, then it actually has an infinite number of ZP extensions. Infinitely many extensions of the field in its algebraic closure have Galois group isomorphic to the p-adic integers. Although if you look at them all together and take their composite, it's just going to be a finitely generated ZP module in some sense, sort of like Z to the n will be like a ZP to the something. And so there are really only a finite number of independent examples of ZP extensions whose composite contains all the others. And there are bounds from above and below on how many independent ZP extensions a number field could have. It's related to the number of real embeddings of the field, that's the R1 of F, and the number of non-real complex embeddings of the field. That's the R2 of F. So a totally real field has no embeddings into C that are not actually into R. So the R2 in that case is 0. And so we think that totally real fields like Q join the square root of 2 or Q should only have the cyclotomic ZP extension as its only ZP extension. And this is known to be true. Yes?
I'm sorry. Two things. Could you remind a student what KPN is?
Oh, sure. Where is that showing up here?
I guess not here, but it's maybe here.
So I'm sorry about that. So there, what I was drawing before, the fields at the different finite layers, when you have your ZP extension of a field, at every finite layer, there's 1 degree P extension, there's 1 degree P squared extension, there's 1 degree P cubed extension, and so forth. And so you usually label those with a 1, 2, 3. The very bottom field, I guess you could call it KP0. It has degree P to the 0 over the bottom field. Okay, so you might label with a subscript n as the degree P to the n extension over the bottom field inside of an extension whose Galois group is the p-adic integers. Okay?
And then there is another question. Can you explain, there's a student saying, why is the Q adjoint the cube root of 2 not totally real?
Good question. So the term totally real is referring to all the possible embeddings into the complex numbers. The field, yes, it's inside the real numbers, but as an abstract field, x cubed minus 2 has 1 real root, but it has 2 non-real roots. Cube root of 2, and then cube root of 2 times e to the plus or minus 2 pi I over 3. And so when a field has embeddings into the complex numbers, not necessarily the identity embedding, that don't land in the real numbers, then it's not totally real. Does that explain why we don't consider this totally real? Like if Q join the square root of 2 has 2 embeddings, but their images in fact are the same, or I gave that other example, Q join alpha where alpha cubed minus 9 alpha minus 9 is 0. That's one field. It has degree 3, but every single root is a real number. And so x cubed minus 2, it has some non-real complex roots.
Good.
Is that okay?
Good, thank you.
All right. So yeah, so if a field is totally real, so there are a lot of settings in number theory where totally real fields have kind of a special behavior. So Liang mentioned totally real fields in the setting of at the end of his lecture. And so here we see another situation where we think for totally real fields, the only possible extension of them that has Galois group ZP is the cyclotomic construction I showed you before. If the field is an abelian extension of Q, like Q or Q join root 2, we know this for sure. In other cases, it's still open. But definitely, if the field is not a totally real field, it definitely has more than one ZP extension. It'll have infinitely many. In any event, so the subject of ZP extensions of number fields was initiated in, I believe, the late 1950s by Iwasawa. And so it's really blossomed. People study Iwasawa theory for number fields, for elliptic curves. In any case, it's a very broad area. It turns out that there are many questions you can ask about, say, finite extensions of Q, where if you would package everything together into an enormous infinite Galois extension, it turns out that the behavior becomes much more accessible to study in the same way that there are some questions related to, say, arithmetic modulo powers of P, where it's easier to work in the p-adic numbers than to work at finite levels mod P, P squared, P cubed, because algebra in the p-adic numbers is much nicer. It's an integral domain. There's no funny divisors of 0 and other things. Polynomials of degree n have at most n roots. This doesn't have to be true in modular arithmetic unless you're working mod of prime. So there are many situations where working with a full infinite extension gives you access to prove things that would be very hard to do individually. And so Iwasawa theory is kind of this idea, exploiting this to study infinite towers of objects as an infinite tower in its own right and taking advantage of that structure. Okay, so let me say something about how the topology on Galois groups manifests itself if you want to, say, map the group continuously into matrix groups. This is the subject of representation theory. People study the actions of groups on vector spaces, or equivalently, homomorphisms of groups into matrix groups. And when your groups are infinite with a topology, then of course you usually want to study continuous homomorphisms, or we say continuous representations. Well, it turns out, even if your Galois group is infinite, a continuous homomorphism to a complex matrix group must have only a finite image. So these kinds of homomorphisms show up when you're defining, for example, Art and L functions. And so these are called Artin representations. It just means a continuous homomorphism to GLN of the complex number. So this is the n by n invertible matrices. Invertible complex matrices. And so Y is a continuous homomorphism from an infinite Galois group going to have a finite image. So by the meaning of continuity, since the identity goes to the identity, then if you take any open neighborhood around the identity in the target, there has to be an open neighborhood around the identity in the domain that gets mapped inside of there. And so you can find a small neighborhood of open set around the identity in GLNC that has no subgroups other than the identity itself. So I had mentioned this last time in the setting of the real numbers or the unit circle, where, if you pick an open neighborhood around the identity, you can arrange that it has no subgroups besides the trivial subgroup. And so what that means then, by continuity, there has to be an open neighborhood of the identity on the left side in the Galois group that gets mapped into there. But in Galois groups, the identity has a system of open shrinking neighborhoods that consist of actual subgroups, right? The subgroup fixing larger and larger finite extensions. And so there has to be a finite extension F inside the field extension L over K, where the automorphism is fixing F. It's an open neighborhood of the identity. For a suitably large F, that's got to be inside of the inverse image of U under rho. But now if you go backwards and apply rho to that, well, that's a subgroup. And so its image is a subgroup of U in GLNC. But our open neighborhood of the identity had no subgroups other than the trivial one. So in fact, that neighborhood of the identity in the Galois group that get mapped into U, as the image is a subgroup, the only option is it's just constant, which means on every coset of this subgroup, the value is constant. You could say that rho is a locally constant function because everything has a neighborhood by cosetting it with one of these groups, and for one of them, it's always 1, and so the coset always has the same value everywhere. But in a compact group, like the Galois group, every open subgroup has only finitely many cosets, finite index, and so therefore rho is determined by its values on the cosets, and only finitely many cosets, you only have finitely many values. So in fact, a continuous homomorphism from an infinite Galois group, or a finite Galois group, in that case is easy, into a group of complex matrices using their natural topologies automatically has a finite image. Now, what that's basically telling us is the topology on Galois groups doesn't really interact very well with the topology on kind of classical topological groups, Lie groups over the real and complex numbers. So let's switch gears and look at a continuous homomorphism into a p-adic group. And we'll see that we get a representation with an infinite image instead of a finite image. So let's just take the group G sub Q, the Galois group of the all algebraic numbers over Q, and let's see how the things behave when I look at them on p power roots of unity. So when you apply an element of the automorphism group of Q bar over Q to p power roots of unity, well, it's going to send them to other powers of that p power root of unity, and the exponents you get as you ramp up the order of the root of unity, the exponents have to be compatible when you compare at the same level. And so you can describe the action by raising to a single number that's a p-adic unit that maybe has different manifestations at different finite levels, but kind of a single p-adic unit. And so associating to looking at the action of an element in GQ on all the p power roots of unity gives us a p-adic unit, A of sigma. And so associating sigma to A of sigma, well, that's a homomorphism. Okay, so when I say chi sub p of sigma is A of sigma, what does that mean? I'm basically saying it's the number by which sigma affects all the p power roots of unity. Okay, by looking at them for all n, you link things together and you create a unique p-adic unit. And so if you compose a sigma with a tau, these exponents will multiply. And so this function from the GQ to the p-adic units, this is called the p-adic cyclotomic character. So for example, at the identity, well, you get, of course, exponent is 1. Complex conjugation, well, the exponent is -1. You know, zeta bar is zeta to the -1. Now, it's hard to give a formula anywhere else because we can't write down elements of infinite Galois groups very easily. I've said this before. Though I also did say before that in this last lecture, I would indicate a sense in which you actually can sort of write down a formula for some elements of this mysterious group. And so we'll get to that at the end of the lecture. But for now, this, it's great to make a definition, but it's totally unclear how you would actually do anything with this because it's hard to say what a formula is. In any case, we'll see that at the end of the lecture. So it turns out that this mapping, by looking at the action of automorphisms just on the p power roots of unity, that every element of ZP star occurs in this way. And in fact, this is continuous. The reason it's continuous, to check that a homomorphism is continuous, for example, if you look at the inverse image of 1 plus p to the n ZP. So in ZP star, the number 1 is inside 1 plus p ZP. That's inside 1 plus p squared ZP. That's inside 1 plus p cubed ZP, and so forth. And so you get this infinite nested family of open subgroups that intersects in the number 1. Okay, so if you wanted to kind of study the number 1 with neighborhood, you can pick these open subgroups. Well, each of these open subgroups, its effect on, if you take the elements in GQ, whose value is there, you're basically looking at the elements that fix zeta p to the n, because that you want the exponent to be 1 mod n. And so the inverse image of 1 plus p to the n in this group is, in fact, the automorphisms fixing the field q adjoins zeta p to the n, and that's a finite extension. And so the group that fixes it is an open subgroup. So the inverse image of basically open subsets are open, and so this chi p is, in fact, continuous and surjective. So here we have a Galois representation with an infinite image. And the fact that we can do that is showing that somehow the topology on Galois groups is much more nicely aligned with the topology on p-adic groups compared to complex groups. Okay. Any questions? No?
Not so far. I'll let you know if something comes up.
Okay. Okay. So so this whole idea of looking at infinite Galois extensions gives us a method to take for every field K, we now have associated to it a compact group, namely the Galois group, or the kind of the maximal Galois extension of K inside of K bar. So the algebraic closure of a field may not be a Galois extension because you may have, like in characteristic P, you could have some funny irreducible polynomials with only one root. So the separable closure of K, that's the name for the biggest Galois extension, the biggest separable extension of K, which all elements have separable minimal polynomials over K in K bar. So the Galois group of that extension over K, that's called the absolute Galois group. So when K is characteristic 0, it is the Galois group of K bar over K. And so, yeah, so we have an interesting method of creating, for every field, some compact group. Its Galois group of its separable closure over itself. So let's take a look at the absolute Galois group of FP. So from finite field theory, sounds like a very strange phrase. From the theory of finite field, that sounds much better. So there's one extension of every degree, and the Galois group is generated by the P power map. So let's call that phi. Whoops. Okay, the P power map. Every automorphism of this field is some iterate of the P power map. And if you iterate this n times, you get x to the p to the n, and that's equal to x for all x in the field. So every finite extension of FP, there's one of every degree, and they're related to each other. Well, I mean, how? You have FP, I should probably draw it a little bit lower. So you have the quadratic extension FP squared. That has its own quadratic extension FP4. That has its own, well, FP to the 8 is not inside of there. This has degree 2. This has degree 2. FP to the 8. Oh, no. Yes. FP to the 8. That has degree 2. Right? It's always very tricky getting the degrees right, confusing the base with the exponent. And so if we could take a degree 3 extension, the degree 3 extension of that, p to the 3 to the 3 is p to the 9, the degree 3 to the extension of that. Okay, so we have all these 3 power extensions and so forth. We could create a degree 5 extension, a degree 25 extension. Excuse me. And so these are degree 5 at every level. And so in all of these, the same function all the time. So this same function generates every finite Galois group over FP. And so what's happening here is, well, let's see. If I wanted to take a look at, for instance, this extension here, and it keeps on going, okay? The Galois group of that extension is actually the 2-adic numbers. The Galois group in this way, so I should not have use a different color here. So the Galois group this way is isomorphic to Z3. And so in fact, you could say, because this element, the peak power function doesn't know that it's only operating on a particular finite field, it makes sense on the entire algebraic closure. This function, you could say it's a topological generator. Of the absolute Galois group of FP. Because in every finite extension, this element, its powers generate everything. So every element, so what this is saying is, if you give me an element in this group, and you look at it on some finite field, it's going to look the same as some iterate of the P power map. And so it's going to lie in the coset of some power of phi. So the subgroup phi, the subgroup generated by phi is dense in the absolute Galois group. And you could say, in some sense, that this group, I just showed you before how, going along different towers of prime degree extensions gives you extensions of FP inside of FP bar with Galois group Z2, Z3, and so forth. And everything is built out of those. You could say, in some sense, I have to be careful not to use the letter P again for a prime number. You could say that this is built out of, it looks like the product of all the L-adic integers for every prime number L. Okay. And so, and inside of here, and this is generated by phi in a topological sense. Okay. So this would be called, this is not a cyclic group, but it has a generator in a topological sense. There's an element whose powers generate a dense subset. Okay. And so that's an important aspect of the structure of this group. It's a pro-cyclic group. Okay. This is often written as Z hat. Z hat. The product of the p-adics, the product of the L-adic numbers for every prime number L. Okay. Another way you could describe it, you could describe the elements of this as infinite series. Whoops. The p-adics have p-adic expansion, so things in Z hat, you could write them as Cn n factorial. Whoops. My tablet likes to guess what I'm writing here. Cn n factorial, where the coefficient of the n factorial, say, goes from 0 to n. And so the point is that n factorial, so a single integer, you just put it into every slot as itself, like the number 1 is 1, 1, 1, 1, 1 everywhere. And so n factorial tends to 0 in ZL for all L, because as the factorial grows, it gets more and more divisible by every prime number, ultimately. And so taking sums of multiples of this, you could write everything uniquely in this way. And so you could say that, so if you called such a thing, let's say it's, I don't know, call such a thing T. Okay, so you call it something like that, T. And then you could say that for, let's say for X in FP bar, you could talk about, I don't know, X to the T, or X to the, excuse me, I didn't mean that. And X to the P to the T. You could raise it not to an integer power of P, but to a Z hat power of P. And so you basically be, X to the P to the C0, X to the P to the, well, C1, X to the P to the 2C2, X to the P to the 6C3, and so forth. Ultimately, these factorials will be divisible enough to make, is this correct? These are ultimately, I wanted these ultimately to become the number 1, and it doesn't look like, okay, I'll be honest, I've never actually done this kind of calculation before in this setting. So now I'm a little bit, yeah, I don't want to constantly be, I don't know how to, I screwed up. I did the same mistake my calculus students do. I don't know how to multiply with exponents. Sorry about that. Yeah, so 2C2 plus 6C3. Yeah, right. Okay, good. And so forth. And so ultimately, those exponents divisible by n factorial, but x to the p to the something will eventually become the identity. And so those eventually don't matter anymore. And so everything's consistent. And so this is a way you could describe the entire group. Oh my God, I really went overtime on that example. I completely, oh dear. So I have 3 slides to go in 3 minutes. Okay. So, so now I want to tell you how to lift that Frobenius thing phi into the Galois group of Q bar over Q. So if you let Z bar be all the algebraic numbers, then an element of GQ will send that back to itself. And if you take a prime ideal inside that massive ring, it's a maximal ideal if it's not the zero ideal. And when you mod out by that, you get a field that actually looks like FP bar, where P is the prime number inside of that prime ideal. So every prime ideal is not zero in that big ring Z bar contains one prime number. And when you mod out by the ideal, you get an infinite field of characteristic P that looks like FP bar. So the Galois group of Q bar over Q acts on all the different prime ideals whose field modulo which has the same characteristic P. And so if you look at the stabilizer of one particular prime ideal, so that's called the decomposition group D of P, then so this is just like in the theory of group actions. You look at the things that fix that P. So this is a subgroup of GQ, and it turned out it's a closed subgroup. And by using it, we can create a characteristic zero analog of those Frobenius elements, generating the Galois group of the finite fields. Namely, if an element of GQ fixes that prime ideal, and there's a lot of these things, it's not just the identity, then it preserves the congruences mod P. Because if two numbers alpha and beta are congruent mod P, then the difference is in P, and so sigma on the difference is in P, and so the two sigma values are congruent mod P. Which means that an automorphism of GQ in GQ that fixes a prime ideal up in Z bar, remember Z bar is is like the integers of Q bar. You can talk about this acting on things mod P. And in this way, you make elements of this decomposition group look like elements in the Galois group of FP bar over FP. And we already told you before what that group sort of looks like. But this group is generated topologically by the Pth power function. And so this mapping of the decomposition group, the stuff that fixes the prime ideal, onto a copy of the absolute Galois group of FP by using Z bar mod the ideal P as a model for FP bar, this is a continuous surjective homomorphism. And in particular, there must be something in it that goes to the Pth power map. And so we call any such thing a Frobenius element at that prime ideal. So a Frobenius element in the absolute Galois group of Q for a prime ideal P up in the algebraic integers is anything that, when reduced modulo the ideal P you started with, looks like the little Pth power map, where little p is the prime number inside the ideal. So as an example, if you apply this Frobenius to a root of unity whose order is not divisible by P, it has to go to a power of itself, but also mod P, the ideal P, it goes to a little Pth power of itself. And roots of unity of order not divisible by P, when you mod out by an ideal that contains the prime P, they cannot start being congruent to each other. So in fact, a Frobenius element at a prime ideal lying over the prime number of P has to, on roots of unity of order not divisible by P, has to send them to their Pth powers. And so in this way, you can discover what, for example, the different cyclotomic characters look like on Frobenius elements. Okay? And so the last thing that I wanted to mention, just to tie some things together, is that there's a theorem in algebraic number theory called the Chebytarov density theorem that says that in a finite Galois extension of Q, every element looks like a Frobenius element, sort of in the sense I just described, but there's a way of talking about it for finite Galois extensions also. But what that means then, in the setting of Q bar, is that every element of Q bar, if you restrict it to a finite Galois extension, it looks like it's close to an actual Frobenius element in the sense that I just described in the previous slide. And when two things are in the same coset, they're kind of near each other. And so basically, that means that the Frobenius elements in GQ are a dense subset. And so this is kind of cute, because when Chebytarov proved what's called his density theorem, it was just a theorem about finite Galois extensions of Q. But from this point of view, it's actually telling us that these very important Frobenius elements in GQ are a dense subset. And that's why when people talk about representations of Galois groups, they're always talking about how it looks on Frobenius elements, not on other stuff, usually. And that's because this is a dense subset, and continuous functions are determined by their values on a dense subset. So that's kind of cool how the notion of density theorem actually has two meanings in this sense. And so I'll stop there. Thanks.